Now let's study the continuity of a function. What is continuity? Or how we can say that a function is a continuous function. The definition is that if the limit at x equals a is equal to the value of the value of fx at a, then we say that fx is continuous at x equals a. And if fx is continuous at every point, on the interval, and we say that fx is continuous at that interval. That's the continuous function, the definition of continuous function, or the definition of fx continuous at one point. From the definition, we know that actually there are three conditions in the definition. The first one, we should define, and the fx should defined at x equals a. That is, if a is defined. The second condition, that is, the limit should exist. And the third one is the limit should equal the value at that point. The limit should equal fa. And by the theorem of existence of the limit, that the limit exists if and only if the left limit and the right limit are equal. The left hand limit equals the right hand limit. So the second condition can be replaced by the conditions for left limit and the right limit. Now we use the definition to determine if a function is continuous at a point or not. The first example is if fx equals 2x plus 3, if x less than 4, 7 plus 16 over 6 over x when x greater or equal to 4. As fx continuous at x equals 4, if we want to determine if a function is continuous or not at one point, we have to compute the left limit and the right limit, because this function is piecewise function. For other function, maybe we just need to find the limit at that point. So for this function, because it's piecewise function, so we compute the left limit and the right limit. The expression for f(x) at x less than 4, that is 2x plus 3. Then x tends to 4, that is 11. And the right-hand limiter, right limit. The expression for f(x) greater than 4, that is 7 plus 16 over 6 over x, that is 11 as well. And f(4), that is 7 plus 16 over x, because the equal sign is here. That's 4. That's 11. So the limit equals the value. So f(x) is continuous at x equals 4. Okay, that's the first example. The second example. That is f(x) equals 1 minus x squared when x less than 1. 1 over x when x is greater or equal to 1. Determine whether is continuous. It's still a piecewise function, so we use the right limiter and the left limiter. X tends to 1 from the left. That is, x tends to 1 minus x squared, that is 0. And when x the right limit, when x tends to 1 from the right, that is 1 over x, that's 1. So the left limit does not equal to the right limit. So f(x) is not continuous at x equals 1. The third example. Find the value of a and b so that f(x) is continuous everywhere. Where x is a piecewise function, x squared minus 2x plus 1 when x less than 0. It's ax plus b when x greater or equal to 0, less or equal to 2. And when x greater than 2, that's 4 minus x. Because for each part of this function, and each part of this function is a polynomial, so the only discontinuous point can be occurred at the point, the joint points. So the solution is we determine if the joint point is continuous. So when find the left point and right point at x equals 0 and x equals 2. The left limit at x equals 0, that is x squared minus 2x plus 1, and take the limit, that is 1. And the right limiter at x equals 0, that's ax plus b. When x equals 0, that's 1. So if the function is continuous, the left limit should equal the right limit, so that is b equals 1. And then for x equals 2, we take the left limit as ax plus b. B is 1, and then takes x tends to x approaches to 2, that is 2x plus 1. And the right limit at x equals 2 at the right of x equals 2, the expression for fx is 4 minus x, so that is 2. So the left limit equals right limit, that result to 2a plus 1 equals 2. We solve for a, that a is 1/2. So if x equals 1/2, a equals 1/2, a equals 1/2, b equals 1, fx is continuous everywhere. That's the continuity for a function. And if any of these three conditions if any of these conditions, any of these three conditions is not satisfied, then it corresponds to a discontinuous point. The discontinuous points can be there's 4 types of discontinuous points. Can be categorized by the discontinuous points can be categorized by the limiter, whether the limiter exists or not. The first type of discontinuous point is when the limit exists, but if A does not define, or if A does not equal to the limit. This type of discontinuous point called removable. Removable discontinuous point. Why we call it removable? Because if we redefine fa equals the limit, then fx is continuous at x equals a. So we call it removable. By the graph, it should be like this. That's the removable. This point, at this point, fx does not define at this point, or is defined but at other position. That's the removable. If we redefine fa equals the limiter at this point, then it's continuous. The second type of discontinuous point is called jump discontinuous point. That is, the limiter the left limiter and the right limit exist, but not equal. But do not equal. It's called jump or step discontinuous point. Because from the graph it lacks this. The right limiter and left limiter both exist, but does not equal. So there is a gap between these two limits. So it's like a jump from the left jumped to the right. The third type of discontinuous point are called infinite discontinuous point. Either the left limiter or the right limiter is positive or negative infinite. We call this type of discontinuous point as infinite discontinuous point. From the graph, it should like this. This is the graph for 1 over x. At x equals 0, the left the left limit tends to negative infinity, and the right limit tends to positive infinity. Either one of these are called infinite discontinuous point. The last one is both the left limit and the right limit do not exist. It's called oscillation discontinuous point. Because both from the left and from the right don't have limit, that means when x approaches to a, the function is changing its value from time to time. So that's the oscillation discontinuous point. Now let's take some examples let's see some examples of discontinuous point. That's example 4. Yeah. Find all discontinuous points. And determine their type. If it is removable, redefine the value. To make it continuous. The first one is fx equals x plus 2 and over x squared minus 4. The second is fx equals x squared plus 6x plus 9. That's the absolute value of x plus 3. Solution that is for fx, the first one. Fx does not define at x equals positive and negative 2. Other points are all defined and continuous. For x equals 2, that is x plus 2, x squared minus 4, that is x tends to 2, as x plus 2, x plus 2 over x minus 2. We cancel the common factor. Then its limit becomes x tends to 1 over x minus 2. So this limit equals negative infinity when x tends to from the left of to the left of 2, because x from the left of 2 then x is less than 2. The denominator is less than 0. It's negative, so positive over negative is negative, and x minus 2 tends to 0, so that is negative infinity. And when x approaches to 2 from the right, is positive infinity. So fx, so x equals 2 is an infinite discontinuous point. When x equals negative 2, x approaches to negative 2. That's x plus 2, x squared minus 4, that is x tends to negative 2, that's 1 over x minus 2, that is negative 1/4. So x equals negative 2 is a removable discontinuous point. And redefine f negative 2 equals negative 1/4. Then fx is continuous at x equals negative 2. That's the first one. The second one, fx equals x squared plus 6x plus 9 over the absolute value of x plus 3. There's absolute value of x. So the absolute value, we take out, get rid of the absolute value. That means x squared plus 6x plus 9 when x over x plus 3. That when x greater will be equal to 0. And x squared plus 6x plus 9, that's 3 minus x when x less than 0. So the only there's actually that's different. The only discontinuous point can be occurred at x equals 0. Other x, for other x, fx is continuous for any other x. So we just need to take care, pay attention for x equals 0. X tends to 0, the left part, the left limit, that's x plus 3, that is 3. And the right, from the right, that is the deal equals 3. So there's no x tends to 0. Fx from the left equals from the right equals when x equals 0. So there's no discontinuous point. There's no discontinuous point. Okay, now we have the infinite discontinuous point, removable discontinuous point, and we look for another example. Look for example for jump discontinuous. Fx is 1 plus x squared when x less or equal to 0. 2 minus x when x is greater or equal less than 0. Greater or equal to 0 is here. Less or equal to 2. And when x greater than 2, that is x minus 2 squared. Okay, find all discontinuous point. So we need to compute the limit at x equals 0 and x equals 2. First, find the left limit and the right limit at x equals 0. The left limit at x equals 0, that is 1 plus x squared. The limit of 1 plus x squared, that is 1. And from the right, right 2 minus x, that is 2. So the left limit does not equal the right limit. So x equals 0 is a jump discontinuous point. That's the left limit and the right limit at x equals 0. Now we look for x equals 2. From the left, the limit from the left of 2, that is use the expression 2 minus x, because x is less than 2. That is 0. And from the right is x equals the fx is x minus 2 squared. So that is 0. So the left limit equals the right limit. And fx is defined at this point. So f2 equals 0. That's defined. So so the function fx is continuous. At x equals 2. That's the continuity and discontinuous point for for a function. Okay, let's stop here.